All right, welcome back again, everybody. Today we're going to be doing section 6.2. This section is all about angles and linear and angular velocity and all sorts of cool stuff like that. Before we can get into a lot of the details of trigonometry, we have to get some comfortability with angles. And I hope you enjoy this one because I've got a lot of tips and tricks for how to make remembering these angles and evaluating trig functions at these angles a lot easier. All right, let me get the slides pulled up and let's go. All right, so we're on section 6.2. Here's the overview. We're going to go through some preliminary definitions. These definitions are pretty straightforward. You've probably heard them before. Things like what is an angle, what is a ray, so on and so on. We're going to talk about how to measure angles using degrees. Then we're going to talk about how to measure angles using radians. Then we're going to talk about converting between degrees and radians, followed by circular arc length. Then we're going to talk about some important angles. So I split these into two categories. The first category is standard angles that you need to memorize. That means commit to memory, memorize these. And then there are standard angles to recognize. These are angles that you don't really need to commit to memory, but you should be able to recognize them as standard angles. And the idea is that you really don't need to memorize much. You just need to memorize a handful of angles, and then it turns out that all of the relevant angles or all of the the nice angles are just multiples of those angles that you memorized. Then we're going to talk about the area of a circular sector, and we'll finish off by talking about linear and angular velocity at the end. Okay, so let's get to some definitions. I'm going to fly through these because I'm assuming you've seen at least some of these before. So what is a ray? Well, a ray is a half line. It's a portion of a line that starts at a point V and extends indefinitely in one direction. V is what's called the vertex. Now, if two rays share a common vertex V, then they form what we call an angle. So an angle is basically the going between two rays like so. One ray is called the initial side, that's where the angle begins, and the other ray is called the terminal side, that's where the angle ends, all right? And the angle itself is defined as the measure of rotation from that initial side to the terminal side. Now, we often use lowercase Greek letters to denote angles. It's just kind of a mathematical convention. So you'll see letters like theta, alpha, beta, and gamma to denote angles. Just assume they're angles for now. It's just a convention. Now, here's one thing that might feel a little bit weird, but if the rotation of an angle is counterclockwise, then the angle is positive. All right, so it's opposite of a clock. So basically, if your angle goes like this, counterclockwise, the measure of that angle is positive. Now, if the angle goes down like this, clockwise, then the measure of the angle is negative. All right. The reason for that is just the way that we order the quadrants. You know, it goes like one, two, three, four. Maybe I'll just sketch it out real quick. Right, this is quadrant one, two, three, four. And so that's why the angles are positive when they're measured counterclockwise. That's the idea. So on this figure that you see right here, the angle alpha is positive and the angle beta is negative, just like so. All right, angles can include full rotations, so keep this in mind. Full revolutions, angles can go all the way around and then come back. They can include any number of full rotations all the way around. I mean, this is an angle here. That's a valid angle, for example. More importantly, and maybe more algebraically speaking, an angle theta can be any real number. So when we're talking about angle measures, angles can be any real number, all right? Doesn't matter if it's negative or positive or zero, doesn't matter if it's irrational, rational, an integer, it can be any real number. So geometrically, what's happening is we're basically taking the real line that we're used to, and we're anchoring zero at the initial side of an angle and then we're wrapping the real line around in a circular path, right? So you could think of set this as like the 0 point, and then this way would be positive, and this way would be negative, and we're just wrapping it around infinitely, wrapping the whole real line around that way. Now, most of the time, we're actually going to put our angles in what's called standard position, where we take the vertex and we place it at the origin of the XY plane. That's going to help us convert between planar geometry and coordinate geometry, as you're going to see in the next section. Standard position just means that we put the vertex of the angle at the origin. That's all. We're going to have the initial side corresponding with the x-axis, and the terminal side will correspond to wherever the angle ends. All right, so angles and quadrants. So when an angle is in standard position, the terminal side will either lie in one of the quadrants, in which case we say that the angle lies in that quadrant, or it will lie on an axis. And if it lies on an axis, we call that a quadrantal angle. And we're going to see some examples of these, lots of examples of these in just a minute here. All right, so those are the preliminary definitions. I hope those aren't too bad. Next, we're going to talk about degrees. So the first way of measuring an angle that we're going to describe is called a degree. And here's the definition. The angle formed by one revolution, meaning rotating the initial side exactly once in the clockwise direction until it coincides with itself. That full rotation there is chosen to have a measure of 360 degrees, these things that we call degrees. I have a little note here. The choice of having it be 360 is a little bit arbitrary, meaning there's not a, well, how do I say this? We could really pick it to be any number that we want, but people chose 360 a long time ago for a lot of reasons. One, it has a lot of factors. 360 has a lot of factors to it. There's also about 360 days in the year. So it corresponds to a nice full year of rotation if you discount the extra 5 1/4 days there are after that. So that's why it's 360. It's kind of a historical choice. We denote degrees using a little circle superscript there. And 1 degree is equal to 1/360th of a revolution. So one whole revolution is equal to 360 degrees. So 1 degree is equal to 1/360th of a revolution. So 1 degree is a very small angle. All right. Okay. Now we're going to practice a little bit. We're going to draw these in standard position. And I think what I'll do is I will do the first two, and then I'll leave you to do the second two on your own, okay? So let's take a look at the first two. Where exactly is 135 degrees on the plane, right? Where does that angle lie? And then we'll look at negative 180. So here's 135 degrees. And just keep in mind that a full rotation is 360, right? So if you start thinking about the full rotation as 360, we're going to chop that up into a bunch of little pieces. So if the full is 360, half is 180, right? That's half of 360. And then if we were to take 360 and cut it into four, we would get 90, right? Like 36 divided by 4 is 9. So 360 divided by 4 is 90. So this angle right here is 90. Now, 135 is going to be bigger than 90, but it's going to be less than 180, right? Oops, there's 180. And in fact, 135 is equal to 90 degrees plus 45 degrees. So we're going to go a little bit past 90 degrees, and then another 45 degrees, and that'll be 135 degrees. So that's where that angle lies right there. Now, this angle, negative 180, the thing I want to point out is that it's negative. So that means we're going to measure it in the clockwise direction, right? So it's going to go this way, 180 degrees. And like I mentioned a minute ago, 180 is half of 360. So it's going to be half of a full revolution, just like that. Okay. Now I want you to think about the other two. One of them I kind of already gave you, and the other one kind of builds off of one we already saw. So what I want you to try on your own is drawing these two angles in their standard position. All right? So think about it for a minute, and then you know what you got to do. You got to say something out loud. Maybe just describe what you know about this angle and what you can see about this angle. Just say anything out loud to give your brain that feedback and get the juices flowing. Right. Now try to draw them. Just a quick sketch, doesn't have to be precise. The idea is that you just kind of want to recognize where these angles would lie on the XY plane. All right, now let's take a look at them together. So here is a 90-degree angle. Those always play a special role in things. Right angles, 90-degree angles. So here's the initial side, terminal side, there's 90 degrees. Now, 495 degrees is actually a full rotation, 360 degrees plus another 135. So this angle is going all the way around once and then continuing to go around 135 degrees. So the angle or this ray is going to coincide with the ray that lays at 135 degrees. But the difference is you went all the way around. So one important point I want to make, because this tends to throw people off a little bit when they first start working with angles, these are 495 degrees is not equal to 135 degrees, all right? Just because the rays coincide doesn't mean that the angles are the same. Just keep in mind that angles correspond to real numbers, all right? So you wouldn't say something like, oh, here's an example. You wouldn't say 1.5 is equal to 0.5, right? So even though they both have a decimal point or a decimal representation that has a point 0.5 in it, that doesn't mean they're the same number. So 495 is not equal to 135, even though the rays coincide. All right, just keep that in mind. All right, now that we've talked about degrees, let's talk about a superior way to measure angles called radians, all right? You'll see why radians are better as we go along, but here's how we start. Recall that the formula for the circumference of a circle is 2 pi r. This is definitely a formula you want to have memorized. Hopefully most of you have it memorized or at least kind of remember it from the past. It shows up a lot because it's so fundamental. But check this out. This is the formula for the circumference of a circle. It's 2 pi r. And what this means, maybe more intuitively, is that the circumference of a circle is proportional to its radius, right? And the constant of proportionality is 2 pi. So if you want to get to c, you take the radius and you multiply it by 2 pi. So the circumference is proportional to the radius, and that proportionality constant is 2 pi. Maybe more specifically, we can say that right there. Now, put another way, using our fundamental intuition of fractions, we can say that the radius of a circle fits inside the circumference of the circle 2 pi times, quote unquote. Uh, One little note I have here, 2 pi is approximately 6.28. I'm sure all of you have heard that pi is about 3.14. We also explored that earlier in the first chapter. So 2 pi is about 6.28. So what this means is that the radius of any circle can fit inside the circumference about 6.28 times. All right. Now, here's another cool thing. If our circle is actually the unit circle, remember the circle with radius 1, then the circumference is just equal to 2 pi, because now 2 pi r is 2 pi times 1. So we just have 2 pi. And this is actually what's going to lead us to a very natural way of defining a new angle measurement called a radian. So here we go. So what is a radian? We're going to make some sense of it here, but let me at least read this definition. A radian is a unit of angle measurement such that 2 pi radians corresponds to one whole revolution. All right. An angle that measures 1 radian subtends an arc on a circle that is 1 radius length. Okay, now this is a bit weird at first, but there's a really, really nice animation here made by Lucas Vieira, and we're going to look at it in just a minute. But let me talk about this figure over here. The main thing you want to remember is that a full revolution, one full trip around the circle, that is 2 pi radians. Okay, so we're going to measure the angle as 2 pi radians going all the way around. And 1 radian is about this angle that you see here. So that's what 1 radian looks like. Now, how is this coming about? Where is this, like, what's the crux of this definition? We're going to take a look at this animation right now. Let me pull it up. Okay, here we go. All right, let me reload this. Oops, hey, come here, come here. There we go. Ah, okay, let me try that again. Let's start this over. All right, so here's the beginning of it right here. There's a circle swept out, radius r. And what we're going to do is we're going to take that radius and we're going to essentially slap it onto the circle like so. and we're going to measure that angle. And that angle is 1 radian. Okay, that's 1 radian. Now check this out. There's 2 radians, there's 3 radians. Half of a rotation is pi radians. And then a full rotation is 2 pi radians. And that's where that's coming from. That's where that's coming from. So I want you to just kind of stare at this for a minute. I'm going to let it replay once, maybe twice. You can also follow along by following that link and check it out on your own. But this is the way that we're defining a radian, and this is why we're defining it the way we are. You take that radius, you slap it onto that circle, and that gives us 1 radian. That's 1 radian. 2 radians, 3 radians, pi radians, and then when you go all the way around, you get 2 pi radians. There it is. Okay, so that's how we're defining radians, and we're going to see why they're superior again in just a moment here. Let's get back to the slides and take a look at what's next. Okay, so like you had kind of seen in the picture, we can convert between degrees and radians, and that picture is one of the things that's going to help us do that. So 360 degrees with a full revolution, and 2 pi radians was also a full revolution. So we have this equality right here. 360 degrees is 2 pi radians. And from that equation, it follows that pi radians is 180 degrees. Now, this is like the anchor for everything else that we're going to talk about in regard to radians, all right? It's like the anchor. So whenever you think of 180 degrees, you should also be thinking pi radians and vice versa, all right? Same thing. This is an equality. They are actually equal. You can interchange them willy-nilly. You can interchange them anytime you want. It just depends on the context. So from this equation, we can basically divide stuff on either side, or both sides, I should say, and we can get a formula for 1 degree. So 1 degree is pi over 180 radians, and 1 radian is 180 degrees over pi. You can get those formulas from this formula up above. All right. Okay, now what might come as a surprise or might feel a little bit weird at first is we assume all angles are measured in radians from now on, all right? Not degrees. So if you ever see an angle, you assume that it is given in radians, unless it is specifically denoted with the degree symbol, that little circle, right? That degree symbol. And again, we're going to see why in just a minute. But because of this, we're actually going to omit the notation rad most of the time. Most of the time. Long story short, if you ever see an angle, you assume that it's a radian measure and not a degree measure, unless it's explicitly called degrees. Okay? All right, now let's take a look at this picture. This here, pi radians is 180 degrees. Again, this is like the anchor for all the other angles we're going to talk about. So this is an image that you want burned into your brain. You want to memorize this picture, and this is going to help you memorize all the other angles we get to in just a minute. And the reason is right here, this box. In practice, it's a lot easier to think of a radian angle as a multiple of pi. And we've been setting you up for this since chapter 1, but all these other radian angle measures, you can think of them as some fraction or some multiple of this angle pi. Okay, you're going to see what I mean in just a minute here. Pi is the angle in standard position swept out by the upper half of the unit circle. So you can equate the angle pi with this upper circle right here. This is the angle pi. Okay. Yeah, and this is just what I was saying a minute ago. You're going to think about all the other angles as multiples or fractions of pi, and then working with them is actually very straightforward. You're going to see it's very simple. You got to appeal to counting. This is one of the things I said back on day 1, and we talked about a lot back in chapter 1. If you can appeal to counting, do it. It'll save you a lot of work. All right. So let's do this. Let's see, which ones do I want you to try? Hmm. Well, okay. Try this. Well, try this. I want you to try to convert these two angles to radians, and then I want you to try to convert these two angles to degrees, and then we'll do them all together, okay? So think about it for a minute. Take a look at these, those and those. Now, say something out loud. What I would recommend is that equality, that conversion relationship between radians and degrees. What is it? All right. And now try to work those two out. All right. Remember, the conversion is that pi radians is 180 degrees, and that'll get you all the rest that you need. Okay. Now let's take a look at it together. And I have all the other ones on here too, but I want to walk through them piece by piece just to kind of show you the reasoning for how to work with these things. So 30 degrees is actually a standard angle, and that's gonna be one that you're gonna memorize. We'll get to that in a minute too. But remember, there's that conversion formula that 1 degree is equal to pi over 180 radians. So we're gonna take 30 and we're gonna multiply it by pi over 180. Essentially, we're changing the units, right? We're converting the units from degrees to radians, and this is the scalar that's going to allow us to do that. Now we just need to do a little bit of arithmetic, and here what I'm doing is putting the number, I'll say the integers together as so, and reinterpreting this as 30 over 180 pi's. Well, 30 over 180 is 1/6, so this is going to be pi over 6, and we have that 30 degrees is pi over 6. Now, here's what gets fun about this stuff, or at least I think this is a little bit fun. Once you know some of these standard angles, like 30 degrees is pi over 6, other angles that are multiples or fractions are actually easier to convert. You don't always need to go to this scalar, this conversion factor. You can use what you know about the other angles, and it will save you a lot of time. So, like 15 degrees is half of 30 degrees, but 30 degrees is pi over 6. So that means 15 degrees has to be pi over 12. That's it. It's literally half. This is half of this. So this is half of that. And I literally just did 1/2 times pi over 6. So don't feel compelled to always go back to this conversion factor. Use what you know about the standard angles and go from there. I'm going to continue this way before I get to these. So now what is 200 degrees? Well, this one we'll just use the conversion factor. 200 times pi over 180. Then you can reduce the fraction, cancel some common factors, and this is actually 10 ninths pi, so 10 pi over 9. So 200 degrees is 10 pi over 9. Now, what about negative 150? Remember, we can have negative angles. Well, 1 degree is pi over 180 radians, so we do negative 150 divided by 180, and we get negative 5 pi over 6. Okay? All right, now we're going to convert the other way. So now we're going from radians to degrees, and just remember this. This is always the thing you want to fall back on. Pi equals 180 degrees. So what that means is literally wherever you see pi, you can replace it with 180 degrees. And then just massage everything to get all the kinks out, cancel common factors, simplify. All right. So this ends up becoming 675 degrees. What is pi over 7? Again, I'm replacing pi with 1 and 180. And this, well, 180 isn't divisible by 7, so that's actually as simplified as it's going to get. But if you wanted to approximate it, if you wanted a decimal approximation, you could just say that it's about 25.7142 degrees. And using a similar technique that we saw with these two, if I want to know what pi over 14 is in degrees, well, that's half of pi over 7. And I already know what pi over 7 is approximately, so I'll just divide this by 2. I'll take half of pi over 7, and that'll give me about 12.8571 degrees. All right, then again, negative angles are allowed. I see a pi here. I'm going to replace it with 180, and that actually does simplify to negative 108 degrees, just like that. Okay, now, that's converting between degrees and radians, but I want to make this a little more intuitive, and I want to bring in some helpful pictures to make this easier to do. These are essentially units. It's a new way of measuring things, and anytime you learn a new unit or a new way of measuring things, you want to get comfortable using it. Think about like when you first learned about centimeters or inches or meters versus yards and so on. It just takes a bit of practice and meaningfulness to make it easy to work with. So here, this might seem like a quote easy question, but I want you to think about it carefully and work it out. And there's a similar question on the homework where you will have to do this. So I do want you to try this one on your own, and I want you to represent these angles as multiples of pi. All right. So thinking back to section 1.1, remember if you have a fraction a over b, you can always rewrite it as 1 b of A, this is what I'm talking about. So I want you to rewrite these or re-represent these as multiples of pi, okay? So ponder that for just a minute, okay? Now verbalize it, say something out loud about what you might try, even just the first one, and then work all of them out on your own, and we'll do it together in a moment. Okay. All right, let's take a look at this now. So the idea is really quite straightforward. Pi over 2 is half of pi, to give you an example, right? It's just half of pi. So if we have a visual representation of pi, we now can have a visual representation of half of pi. This one here, this is a quarter pi. So if we know what pi looks like, now we can visualize what a quarter of pi looks like. This one is 3/4 pi. This one is 2/3 of pi. This one is 7/4 of pi. Notice that 7/4 is actually bigger than 1, right? It's 1 and 3/4 of pi, which is okay. Oh, sorry, this is an equal sign, which is okay. We can have more than one pi, right? Who doesn't like more than one pi? This is 1 and 3/4 pi. And this one here, this is 5/3 of a pi. Oof. So that's what? 1 and 2/3 of a pi. And that's the idea. So these angles, as they're written here, they may not feel as intuitive, like, oh man, 2 pi over 3? Oof, that feels a little like it's hard to work with, right? But if I think of it as 2/3 of pi, suddenly it clicks. And we're going to make it click even more by looking at these images right here. So pi over 2 is half of a pi. Remember pi. Pi is the full upper half circle. That's the picture you want to have burned into your brain, that's pi, right? That's pi. We're going to think of everything as some fraction or a multiple of that picture right here. So what is half of pi? Quite literally half of that upper semicircle, right? What is a quarter pi? It's a quarter. So this is where it gets really fun, I think, right? So here's the upper semicircle, that's pi. We're going to split that into 4 equal-sized pieces. 1, 2, 3, 1, 2, 3, 4. And we're just going to take one of those pieces. Remember the fraction, the numerator, or sorry, the denominator tells you how many pieces you were cutting it into, and the numerator tells you how many of those pieces you've got. So we're cutting this into 1, 2, 3, 4 pieces, cutting pi into 4 pieces, and we're taking one of those pieces right here. So this angle is pi over 4, or a quarter pi. Moving on. 3 pi over 4? Feels weird. 3/4 of pi, got it. 1, 2, 3, 4. I'm going to take 3 of them, and that's the angle 3/4 pi. How about 2/3 of pi? Now we're going to split pi into 3 equal-sized pieces. Ready? 1, 2, 3. And we're going to take 2 of those pieces. 1, 2. So that's our angle 2 pi over 3, or just 2/3 of pi. Pretty cool, huh? Let's check out the next one. See, now we've got more than a whole pi, right? Remember, this is pi. Let me redraw it up here. There you go. That's pi. Now we've got 1 and 3/4 pi. Okay, so that means we have a full pi, and then we have 3/4 of that pi. 1, 2, 3. So the angle 1 and 3/4 pi actually goes all the way to here. It's that angle. What about 1 and 2/3? Same idea, except now we're going to cut pi into 3 equal-sized pieces. 1, 2, 3. And we're going to take 5 of them. 1, 2, 3, 4, 5. So this angle is 5 pi over 3, or maybe better realized as 5/3 of pi. 5/3 of pi. Cool stuff, huh? Appeal to counting. Use pi. Use pi. Cut pi into pieces and count the pieces. It'll make your life way easier, trust me. Okay, now let's talk about circular arc length. So this is one of the reasons that radians are superior to degrees, all right? They're superior because not only do they provide an angle measure, they also provide a circular arc length measure. Degrees do not do that. Degrees only carry angle measurement with them. They don't carry length with them the way that radians do, all right? So, more specifically, since we know that a full revolution around any circle is 2 pi radians in angle measurement, we get the following formula for the length of a circular arc. Check this out. So, if we've got a circle of radius r, and we sweep out an angle of theta radians, then the length of that arc that is swept out is simply r times theta. So the length, we use the letter s to denote the length. You'll understand more why we do that when you get into calculus. Uh, yeah, I'll just leave it at that. But the length of that circular arc is just the radius times the angle. And this is the beauty of radians, right? This is the beauty of radians because if you want to know this length, you just need to know the radius of the circle and multiply theta by that radius. So it scales, right? The length scales with radians and it scales with the radius. And that's why I have this picture right here. So here, this is the radius r. This is the angle theta. If you want to know how long this circular arc is, you just multiply r and theta and that'll give you the circular arc length, okay? Um, Before we do an example of this, I do want to say this is a formula you want to memorize. Hopefully it's not too hard to remember. It's just radius times the angle, and that'll give you the length, but it's going to show up a lot, so do make sure you have this one memorized. Okay, now that you've got that memorized, just kidding. Um, Try to do this question. Let's say you've got a circle of radius 7 and an angle of 3/4 pi. What is the length of the circular arc swept out by that angle on that circle? Right? Think about it for a minute. Okay, say something out loud. I'd recommend trying to repeat that circular arc length formula that we just saw. Say it out loud to give your brain that remembrance. Okay, and now try to work it out on your own. Do the computation, leave it in exact form. We'll do it together in a moment. Okay. All right. So we're just going to use the formula S equals R theta. We're given R, we're given theta. So what do we have? 7 times 3/4 pi is 21/4 pi. And that is how long that arc is. That's how long that length, that arc length is. Okay. Now, we've got a pretty good foundation for things, but now we're going to really get a great foundation for everything else. We're going to talk about some standard angles that you need to memorize. So, in order for all of the trigonometric ideas that we're going to talk about in this chapter to be accessible, there are some standard angles whose radian and degree measure you've just got to memorize. The good news is it's not many. So, yeah, these are angles and pictures that you want to commit to memory because they form the foundation for other angles that you should recognize. Now, just a little bit of a word to students that are learning this the first time. Beware of what you look up online about this because one of the issues I find students have when they learn this stuff is you can go online and you can find a picture of the unit circle with every single important angle labeled on that circle, every single important angle in radians and degrees and the sine value and the cosine value, and it's just a big, huge mess of information. Do not try to memorize that, okay? Please do not try to memorize it. You can try it, and then what'll happen is you will forget it the moment this semester is over, and you'll have to relearn it all over again. Don't base your understanding of angles and all of this trigonometric stuff off of memorizing that unit circle. Just memorize a couple of important angles and then use that to do everything else. Okay. You know how I feel about memorization. I hate it. So just a tiny bit of memorization can carry you really, really far in trigonometry. So take my word for this and actually don't. Just you'll see as we go through the chapter. So here are some standard angles to memorize, and we're going to look at them carefully. Let me switch to the zoomable slides here. Okay. So first angle you should have memorized is 0. Uh, 0 looks like this. 0 radians is 0 pies, and that's 0 degrees. So this is the angle 0. The next is pi over 6, which we saw a moment ago, and that's 1/6 of pi. You're going to see this played out a little more in the next couple slides. But again, we're taking 1/6 of pi. So take the whole pi, cut it into 6 equal-sized pieces, and then take one of them. That's pi over 6, which is equal to 30 degrees. So you want to memorize this. Basically, this is what you're memorizing, that and this picture, so that you can visualize where that angle lies on the XY plane. Okay, pi over 4, here's another one. Pi over 4, that's a quarter of pi, a quarter pi. Here's the full pi. Cut it into 4 equal-sized pieces. 1, 2, 3, 1, 2, 3, 4. There you go. And take one of those pieces. Pi over 4 is 45 degrees. All right? Next, pi over 3, or in other words, 1/3 pi. Pi over 3 is 60 degrees. How do we find where this is? Well, we take the full pi and we cut it into 3 equal-sized pieces, and we take one of those pieces. That's it. So pi over 3 is 1/3 pi, and 1/3 pi is 60 degrees. Remember, pi is 180, right? Pi is 180 degrees. So if I take a third of that, that's 60 degrees. Now this one, this is a classic one. This is one of those quadrantal angles right here. So pi over 2. Pi over 2 is 90 degrees. Why is that? Well, it's half of pi. Here's the full pi. Here's half of it. And if pi is 180 degrees, then half of that is 90 degrees. So pi over 2 is 90 degrees, and this is what it looks like. And then, of course, this one, which hopefully is already starting to click in your mind. Pi is 180 degrees. So the full upper semicircle, that's pi, that's the angle pi, and it's 1 pi, and that's 180 degrees. Okay? So those are the ones you need to memorize, just those 6. And I'm going to put them here on a single quadrant. So these are the ones that you want to memorize. Basically, all of these standard angles in the first quadrant, okay? Here I've got them all written on one single picture. 0 degrees, 30 degrees, 45 degrees is that diagonal, right? Pi over 3 and pi over 2. Just like that, okay? So this is what you want to memorize. Once you have this memorized, all of the other nice angles, all of the other angles that pop up commonly in trigonometry and beyond are multiples of these angles. Like we might want to do 3 pi over 6s, or we might want to do 10 pi over 4s. But if you know these and you have these memorized, you can just count all the rest. Just count. Appeal to counting, use the fundamental intuition of fractions that we talked about, and it's going to make your life way easier, okay? All right, so now let's talk about some other standard angles that you need to recognize, and I've already talked them up enough already. So this is just repeating what I said a minute ago. You'll be able to deduce these angles from those angles that we just saw. And when we start evaluating trigonometric functions at these angles, you'll be able to use the ones we just saw to evaluate those functions at these angles that we're about to see right now. They're just multiples of those standard angles in the first quadrant. And again, take note of how many pieces there are. Use the fundamental intuition of fractions. So here we go. Standard angles to recognize. I don't recommend you commit these to memory, okay? But you should be able to recognize them. So let's take a look at them. Zooming in. So 2/3 of pi is 120 degrees. But this is easy to compute if you remember that this is 1/3 of pi, right? 1/3 of pi is 60 degrees. So 2/3 of pi is double that, 120 degrees. So this is what 120 degrees looks like. 135, that's 3/4 of pi. 1, 2, 3, 4. We're going to take 3 of those pieces. We saw this earlier, right? So we know what pi over 4 is. Pi over 4 is 45 degrees. Multiply that by 3 and you get 135. That's 90 plus 45. Okay, here we go. 5 pi over 6. 5 pi over 6 looks like this. We're going to take pi, cut it into 6 equal-sized pieces. 1, 2, 3, 4, 5, 6. And we're going to take 5 of them. There we go. Again, we know that 1/6 pi is 30 degrees. So 5/6 pi is 5 times that, which is 150 degrees. All right, 7 pi over 6. Notice now we are larger than 1 pi, right? We got more than 1 pi. Everybody's going to be eating happy. So here, this is pi, and that's 6/6 pi, right? But we want 7/6 pi. So we need one more sixth to get to 7/6. So it's going to pi and then 1/6 more. That's it. But again, if you know what 1/6 pi is, okay, then you know what 7/6 pi is. Just multiply by 7. All right. 5 pi over 4. So now, again, we're talking about angles that are larger than 1 pi. So here's 1 pi, and here's another quarter pi. 1, 2, 3, 4, 5/4 pi. And that's 225 degrees. Again, you don't need to memorize that. You don't need to memorize that. You just need to memorize pi over 4 and multiply it by 5. And that will give you that, right? Pi over 4 is 45. Multiply 45 by 5, and you'll get 225. That's it. Not too bad. Okay, 4 pi over 3, gonna look like this. Again, cutting pi into three equal sized pieces. 1, 2, 3. And we're going to take four of those. 1, 2, 3, 4. And then 3 pi over 2. This is another one of those quadrantal angles. We're cutting pi into two equal sized pieces and taking three of those. 1, 2, 3. There it is. So this is the angle 270 degrees, or 3 pi over 2, or 3 halves of pi, or 1.5 pies. All the same thing. And then 5 pi over 3. So here we're cutting pi into three equal sized pieces. 1, 2, 3. And we're going to take five of those. 1, 2, 3, 4, 5. Check this out. One thing I want to point out. What do you think would happen is if we took 6 pi over 3s? Well, that would be 1, 2, 3, 4, 5, 6. That would actually be a full revolution. And that makes sense because 6 pi over 3s would be 6 over 3 pi, which is 2 pi, which is a full rotation, right? Okay, next slide. Last couple angles to memorize. Here we go. Let me zoom in. I'm sorry, recognize. Sorry, my mistake. Yeah, standard angles to recognize. All right, here's this one. 7/4 pi, 1 3/4 pi. 1, 2, 3, 4, 5, 6, 7. That's one whole pi, and then another 3/4 of pi. So that's where that angle 315 degrees lies, or 7 pi over 4, or 7/4 pi. All right, 11 pi over 6. Now we're almost filling in the whole circle. We're taking pi over 6 and doing it 11 times. Here we go. This is pi over 6, right? This angle right there is pi over 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the angle 11 pi over 6 is down here, or 11/6 pi, and that's going to be 330. Again, just take pi over 6, multiply it by 11, right? What's pi over 6? It's 30, right? 30 degrees. What's 30 degrees times 11? 330 degrees. There you go. Easy peasy. And then the last one, of course, the full rotation is 2 pi, and 2 pi is 360 degrees. So those are all the angles that you should recognize, meaning if you see something like 315 or you see something like 330, you should be like, wait a minute, I recognize that. I'm pretty sure that is a multiple of a standard angle. Let's see, 330, looks kind of familiar. Is it a multiple of 30? Oh, it is. It's a multiple of 30. It's 11. It's some multiple of pi over 6. It's 11 pi over 6s. There you go. All right. So we'll talk about that more in class. We'll practice it more on the activity. Now let's talk about the area of a circular sector, okay? So this is fun. Remember that the area of a circle or a disk, the area of a disk of radius r is pi r squared. This is another one of those basic formulas that you want to have memorized. Everybody should know the formula for the area of a circle. It'll show up forevermore. It's just such a fundamental formula. Pi r squared. Pi r squared. Oh, and if you forget, remember area is two-dimensional, right? Length times width kind of thing. So area is two-dimensional. That's why you have that power of 2 up there. That's related to the dimension of the object, which is something I always find fascinating as a fractal geometer. So suppose we want to find the area of a circular sector that is swept out by some angle theta. You know, like you want to find the area of a pizza slice. So you got a pizza in front of you. What is the area of a slice? Well, how do we do it? Well, what we're going to do is we're just going to take a fraction or a percentage of a full revolution and then multiply that by the area, or multiply the area by that fraction. So a full revolution is 2 pi radians, and the angle that you're interested in is theta. So you're going to take this fraction here, and you're just going to multiply the full area by this fraction. And that will give you literally the area of the circular sector, right? So the area of that circular sector is the fraction of a full revolution afforded by the angle theta. And you're just going to multiply that by the total area. And then you can simplify things, and it actually ends up being 1/2 r squared theta. All right? Okay. And that's where we get this proposition. So that was the proof of this formula. The area of a circular sector with radius r swept out by an angle theta is this formula right here. Okay, now I have a couple notes about this formula, and I'll explain them right now on this slide. So this formula gets used a lot, and in particular, it plays a critical role in Calculus 2 and Calculus 3 when you start talking about the mechanics of the Riemann integral. Uh, Without getting too far off track, when you learn how to integrate in calculus 1 and calculus 2 and calculus 3, you have to basically add up a bunch of things that have the same, we'll say, structure. And this formula turns up when you want to start doing that in terms of what are called polar coordinates in calculus 2 and 3. Okay, so this formula does show up again. Now, this, I feel like, is the more important point. If you forget the formula, I'm all about this. If you forget the formula, just remember the construction. Remember, I'm not a big fan of memorization. What I try to remember is how the things are constructed. And then I don't need to worry about remembering. I just remember how they were built to begin with. And I'm like, oh, yeah, that's how that was built. So that must be what the formula is. So I don't recommend memorizing this. If anything, you should memorize this right here, what I've plotted in, or what I've highlighted in blue. What is the area of a circular sector? It's some fraction of the total area. That's it. Don't bother trying to memorize that. You might forget it. You might forget a whole bunch of things. You might think it's theta squared or something like that. No, no, no. Area of a circle times whatever fraction of a full revolution that angle is. And that's the pizza slice. That's the area of the pizza slice. Okay, you try it. I want you to practice this one on your own. Find the area of a circular sector if the radius is 10 inches and the angle swept out is 40 degrees. All right? So think about it for a minute. Okay. Now say something out loud to your friend, to your peer, your colleague, to your parents, to yourself, just something. Right. And now try to work it out on your own. And before you do, let me give you a little tip. Note that this angle is given in degrees. Okay, now let's do it together. So, like I said, there is a little bit of a caveat here. Notice that the angle here is given in terms of degrees, right? And that formula is in terms of radians. We always want our angles to be in radians. Radians are what preserve arc lengths and areas because degrees just don't do that. Degrees just have angle measurement, right? So the first thing we need to do is we need to convert this to radians. That's the first step. So converting it to radians, we're just going to use the conversion factor pi over 180, and 40 degrees is 2/9 pi. Now, you could use the area of the circle times this angle over 2 pi, or you can just use this right here if you want to just use that. And that's what I used in this. So 1/2 r squared times theta, and then simplify a little bit, massage things, get the kinks out, and then you end up with 100 over 9 pi inches squared. And again, this is an irrational number, so you can leave it like that. That is as exact as it's going to get. It's not going to get more exact than that. All right. Now, shifting gears just a little bit, let's talk about linear and angular velocity. So we're bringing in the notion of speed now. So we're just going to start with a definition or two, and then we'll make sense of it and do an example to kind of show you why it's relevant. Physicists, engineers, you're going to need to know this stuff really well in your major courses because, frankly, circular motion occurs a lot, right? If you can imagine how many things obey or use circular motion in life or engineering or physics, it's a lot. So these things come into play in big ways later on. So let's start with linear or what's called tangential velocity. Suppose an object moves around a circle of radius r at a constant speed right now. For variable speeds, you need calculus. If s is the distance traveled in time t around this circle, or in other words, s is the length of the circular arc, and theta is the measure of the angle swept out, then the linear velocity v of the object is defined like so. And I'll zoom in. The linear or tangential velocity is s over t. In other words, the length of that arc divided by t. But remember, s is r theta, right? R theta. So the tangential velocity is r theta divided by t. That's the formula, okay? Now let's get some intuition for what that is. Get some intuition. The reason that I keep calling it tangential velocity is because it's basically how fast, plus or minus, the object would continue to move in a straight line at any point on the circle. It's basically how fast the object would fly off in a straight line if it left the circle. So a good example is if you're like spinning something around like this at the end of like this pencil, for example, you're spinning it around and then suddenly it flies off. Well, how fast how fast it's traveling when it flies off is the tangential velocity. I've got this little picture here. Maybe I can here, let me do this real quick so I can zoom in a little bit more. Here you go. Oops. No, 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 no. Come back. There you go. Yeah. So here's R, here's theta, here is S. That's the length of that circular arc. And then V, the tangential velocity, is basically that length divided by the time it took to travel that length. Okay. And it's going to go. Pew. So imagine the object flying off. If you want to know how fast it flew off, that's what it is. That's the tangential velocity. That's it. Okay, now let's compare that to angular velocity, which is not the same thing. Angular velocity is this. So you still got an object moving around a circle of radius r at constant speed. If theta is the measure of the angle swept out in time t, then the angular velocity, omega, is theta divided by t. Okay, so let's get some intuition for this one too. The angular velocity is how fast the central angle is changing. That's the difference here. So this is quite literally like the speed of rotation. You can think of it like that. This isn't how fast the object would fly off if it left the circle. This is how fast the angle is changing. It's like the speed of rotation. Notice that it does not depend on r the way that linear velocity does. And I'm going to explain why in just a minute here. Another note with this formula, this symbol, this is the Greek letter omega, lowercase omega. Okay, so it's not a W. It's kind of like a rounded W. I would say that's omega and oop, come back. There we go. And this is W in my handwriting at least. Um, but that's it. So over here I've got another nice picture of it. And yeah, there we go. Nice picture of it. And it's just how fast the angle is changing. So you know an angle measurement, you know how long it took to pass that angle or to traverse that angle. That means that the angular velocity is the angle traversed divided by the time it took to do so, t. Okay, that's the idea. Now we get this relationship. So these, maybe you can kind of tell, these different speeds, these different velocities, they seem to be related in some way. And that's what we're going to distill right now. So this is the connection between angular and linear velocity, all right? So we know that linear velocity is given by this formula, which is r theta over t. Well, we can rewrite it as r times theta over t. But remember that theta over t is the angular velocity. That's omega, right? And so we have this result that the tangential speed or the tangential velocity is r times omega. And this is another formula. All three of these formulas are ones that you should remember. But basically what's happening is this. The tangential velocity of an object moving in circular motion is the angular velocity times the radius. Let me try to make some more sense or make some more meaning of why this is the case. So omega is the angle, I'm sorry, is the speed of the angle swept out. It's like how fast the angle is getting swept out. So think about it like this, and I know you've done this at some point as a kid at least. If you were to rotate, like if you were to spin around, okay, notice that the how fast the angle is changing as I turn doesn't depend on where my hand is. If my hand is out here, right? Pretend there's this pencil, right? If my hand is out here, I'm not turning any faster. no matter where my hand is, if it's close to me, if it's far away from me, close, far, the speed of my rotation is not changing at all. However, think about how fast the pencil is flying if it's up here next to me, okay? Versus if it's way out here away from me, right? Now the pencil is moving a lot faster. The pencil's moving a lot faster, even though the angle of the speed of rotation is not changed, right? There we go. So this is that thing where if you ever did this as a kid where you sit on a spinny chair, right? And you spin around. Well, if you put your hand out and spin around, your finger is going to be flying around, but your head isn't spinning very fast. Your head is just going like, right? So this is why uh, angular velocity doesn't depend on the radius, but linear velocity does. And this is why linear velocity is really just the angular velocity scaled by the radius. It depends on how far out you are from the axis of rotation, right? It depends on how far out you are. And that's why you have that formula. Okay, now let's finish up with kind of a fun example. Here we go. Let's read it together and make sense of it. And then maybe you can try it on your own before we do it together. So here we go. Space Shuttle Columbia orbits the Earth in the path of a circle with an orbital radius of 6,900 kilometers. Okay? The shuttle is orbiting at a rate of one orbit per 90 minutes. That means it goes all the way around the Earth once every 90 minutes. And then suddenly the engines are cut off and the ship drifts off into space. My question to you is, what is the angular velocity and what is the linear velocity in kilometers per hour of the space shuttle at this time? All right. So this one is definitely a thinker. So think about it for a minute. Maybe reread it. First, reread it in your head for a second, right? And now verbalize something. I recommend reading it out loud to yourself, or better yet, your peer, your colleague, your dog, your cat. Just read it out loud to give your brain that feedback. Read the whole thing out loud again, verbally. Okay. And now try to work it out on your own. Remember, angular velocity is angle divided by time. Linear velocity is distance divided by time. Okay. Remember to consider units here as well. It's kilometers per hour, but notice that we're given this measurement in terms of minutes. So keep that in mind, and we'll do it together in just a moment. All right, let's do it together now. So, we know that the shuttle makes one orbit in 90 minutes. So that means in terms of angles, it's traveling 2 pi radians in 90 minutes, right? A full rotation, a full revolution, a full orbit is 2 pi radians. So we know that it's doing that in 90 minutes. Well, 1 hour is 60 minutes. So 90 minutes is 1.5 hours. So our angular velocity is going to be 2 pi radians per 1.5 hours. There's the units right there, 2 pi radians per 1.5 hours. And then when you simplify that, massage things a little bit, move things around, you get that it's going to be 1 1/3 pi radians per hour. So that's how fast the angle is changing, the angular velocity. Now, we have the angular velocity and we are given the orbital radius of 6,900 kilometers. So we can use that relationship between linear and angular velocity to compute it directly, right? It's r times omega. We just computed omega as 1 1/3 pi. Just multiply that by 6,900 and that will give us the linear velocity. In this case, it's ends up being 4 times 2,300 pi, which is 9,200 pi. And then if we wanted to approximate it, because this is one of those times where a decimal approximation is more meaningful, it's 28,902.6524 kilometers per hour. All right. So this is exact. This is exactly how many kilometers per hour. And then this is an estimate, right? This is an approximation. So about 28,000, 29,000 kilometers per hour. That's how fast the space shuttle is drifting off into space. Wild stuff, huh? All right, let's play. Okay, that's it. There's a ton of stuff in this section, so thank you for bearing with it. Remember the tips I gave you? Memorize those angles to memorize. Don't memorize those angles to recognize, and they're going to help you out a lot if you just recognize the structure, appeal to counting, and all that stuff, okay? All right. Thank you all again for watching, and I will see you next time. Take care.